Hi everyone, this is Professor Luchin and this is lecture 17, electrical safety, and I'm also going to speak a little bit about arc flash dangers. Unfortunately, this is a re-recording. My first one was lost by the computer, so let's hope it goes better this time. I don't know if I can take it again. So, electricity is used almost ubiquitously. You turn a switch on and the light comes on. You plug something in and you can turn it on. You see it in the lines that run alongside the interstate. You see power plants. What it can do to the human body is unlike other hazards, in that it travels through the body. There's a lot of conditions and how it travels, the path it travels, and so on and so forth. But basically, what electricity does is, you can almost think of it almost like a microwave. It heats flesh and organs as in its path. And given the amount of voltage or the conditions of the body at the time, which would be resistance, the heating can be accelerated to the point where it almost flashes like blood into a vapor. And that's where it can actually burst out of the person, or cook and severely damage internal organs. So from the outside, the person isn't showing scarring, but the inside of them is basically entering a level of necrosis where it's just going to basically systematically shut down. I think what this picture is, and this is from my friend Todd Cook. He works for Pieper Electric. And he usually does several lectures for me on electrical safety and then arc flash. He does them separately. That this is probably an exit wound from electricity. So there are 4 major injuries when it comes to working with electricity. I guess depending on what type of work you're usually doing a lot of overhead work or a lot of pulling or pushing. So ergonomics, overexertion is definitely there. But electrocution, which is death due to electrical shock, basic electrical shock, burns, or indirect, so falls. So you're working at a height, or usually when you get a shock, it makes you jump back, and that can cause you to fall off a ladder or scaffolding or a roof. So electrical can do a lot of different things. It can also start fires or cause explosions. So I've actually been shocked before. It was basic 120 volt residential outlet. I was changing out a 3-way switch for my father-in-law, and I thought that my tick tracer, which is this device, put it near an electrical source and it picks up electric fields, so you know whether something's been de-energized or not. We thought we had turned off the power. But when I was removing the screw from the original switch, I got hit with one, and it really only stayed within my hand. I believe it was my finger to my thumb, and it made me jump. Yeah, it tingles a little bit. Pain? No, it really wasn't pain. But then we figured out what was wrong. The electricians had labeled the electrical panel wrong. And I also believe they had spliced together 2 circuits that they shouldn't have. So when I found that, I did correct it, and I tried to make sure that I always had a functioning tick tracer. Again, these are only like $10, at the hardware store. I got one with a light, so I can look into a box, because usually it's kind of dark. I also have a continuity tester. This is typically for outlets, but you could do it as long as you can see the poles, like on a switch. You touch both sides, and if this lights up, that means it's live. So the big thing with working with electricity is to respect it, to try to work when it's de-energized. We had talked about lockout tagout. This is just about electricity. You try to work when it's, you should only really work on a circuit or any electrical equipment when it's off, de-energized, locked out. However, there are times in which you have to work when it's on. And under those conditions, then you move to NFPA 70E, in which you use insulated tools, which are more expensive than regular tools. You have to wear more personal protective equipment to protect yourself, not only from shock, but from arc flash, which is a much more dangerous conversion of of electricity, which turns into molten metal and a blast and infrared and all this other stuff, and it's kind of scary. So you got to respect the electricity. You want it to stay within its, in its original circuitry. So in the lines that are overhead or in conduit or underground in conduit or on poles or within your walls. Because as soon as it comes out of those, which are somewhat safe designs, that's when it really becomes hazardous. As soon as you plug something in, it becomes more hazardous. And that's why we don't like to see extension cords in the workplace. Because it's just whatever length it is, it's that length of potential exposure. Should the cord insulation be damaged, or should the internal insulation on the wires be damaged, they could cross over and either melt it and cause a fire or an arc or a spark, or it could shock somebody. What's scary is when it incidentally energizes a metal chassis of equipment or a wire rack or something, and somebody accidentally makes contact and they become part of the ground, and then they get shocked and electrocuted. So in this slide, Todd's showing two possibilities in which there may be improper grounding. The top one, what I see is a strain relief that's damaged, and it looks like there's no clear copper wire. That's usually the ground. And then on the bottom, you see somebody has physically removed the ground prong. A ground line is very important, because if there is some sort of short in the system or some issue with the integrity of the insulation, a ground line is meant to save you. Because Todd would always say that you think for electricity it's the path of least resistance that electricity goes, but what Todd says, it goes through all pathways, but when there's more of it goes through the path of least resistance. So if you have a ground prong and you make contact with it, it would prefer to go through the ground than it would you, but you'll get a little bit of a hit by it. Here's a damaged cord, so you can see the wires within. This type of situation should be taken out of operation, removed. You should really cut the cord and throw it away and get a new one. You shouldn't try to repair something like this. Todd talks about tripped circuit breakers or blown fuses. We typically don't see fuses as much anymore. You may see it industrially, but here's a circuit breaker. It's an interesting device. Very simple. Only the hot wire gets attached right here. So the black wire. And then, so it's off right now, and then you go into a circuit breaker panel or power center, and you see this particular design, and I can't really see who is it, will clip on the outside, and then as you push it, this thing will clip down on a pole that's part of the main power bus. What I mean by that is the lines that come in from the road, they connect to the main power bus. It's the most dangerous part of a circuit breaker panel. So you got to be really careful. And when you connect it, you should have a glove on, and you should be standing, away from or aside from the power center. Push it in. Make sure there's good contact. For the circuit, there'll also be a neutral line that gets screwed into the neutral bar. The ground line gets screwed into the ground bar, and the ground bar then is connected to a thicker stranded copper line that actually goes to a stake that's into the ground. It's where electricity gets dissipated. Once everything is hooked up, you flip the switch, and now it's operational. The circuit is now live until there is a draw more than what this piece of equipment is designed for. This one is designed for 20 amps. So if there's a draw in the circuit that's above 20 amps, it goes to neutral in order to protect. Because if you draw too much power through a line that's designated only to carry so much, and so in this case 20. So if the equipment that I had plugged into this circuit tries to draw more than 20 amps, it'll trip. Because if it was allowed to do that, the lines would heat up. The outlets and components would heat up because it's drawing more than it can, and the excess gives off heat, which could then melt or damage the insulation, creating a chance for fire, arcing, or sparking. So, circuit breaker. Ground fault circuit interrupters, we'll talk about that in a little bit. Here we have tool cords could actually be damaged as well, something to look for. You're supposed to take these out of service. Even if you have, let's say you have a circular saw, and the cord is worn, you can typically buy a replacement, because you just open up the chassis of it, install it at the source, and then you've got a brand new cord. So it can be, you don't have to throw away the circular saw, but you just have to replace the cord with a brand new one. What's interesting about it, and this is something that I had learned, I kind of fancy myself as sort of a journeyman electrician. I worked for Home Depot for like 6 months in the electrical department, and doing that, I was working with other people who were doing electrical work, and they were teaching me what they were doing. And then when contractors came in and they needed help finding things, I'd help them, but then I'd have them explain it to me. So I was like training and learning it. And I also had just purchased an older home. It was a starter home, and I was learning to do the work there as well, which is why I started getting, the tools like the tick tracer and continuity. I also had this device I could plug into any outlet, and it lets me know, it tests its ground and it tests its polarity. What the polarity is that the hot line is connected to the hot pole and the neutral line is connected to the neutral pole. You wouldn't see much of a performance difference other than more things can go wrong. But it also checks ground, so that's an important thing as well. I also have my trusty wire cutter, and I'm not going to do too much more with that. But as you see on the screen, the gauge of the wire, here's a 12-2 Romex. The gauge of the wire dictates what is the maximum amperage that can be drawn through it. So it shows here, so again, this is a 12. A 12 is designed for 20 amps. A 14 gauge is designed for 15 amps. And so the greater the amps, the greater the size of the cord. The larger the gauge, the lower the voltage. And so when you get up, like the 18, 19, 20, you're now talking like speaker wire, things like that. And this is considered rigid. It's a solid piece of copper here. So here's the hot, it's black. Here's the ground, it's no covering, and then we've got the neutral, which is white. And we do that so that when we hook it up in two different places, we know which line is which. Sometimes we got more wires than this. We use that, for carrying double power if we need more to an outlet or a switch. Or if we're going to do like a three-way switch, where when you've got a room and you get a switch on each side, you have to, one of the wires then becomes something called a traveler switch. And so as the switches change, in one condition it's on, in another condition it's off, and the traveler switch allows you to achieve that. So the 0 is the largest, and that's called knot. Sometimes you can buy wires that are double knot. Double knot would be something like that comes from the outside the home into the home, and usually you have two wires that come in. Then you can see those, they go into the side, and they come down into the power center or the circuit breaker panel. It connects to the main hot bus, and then you've got all the switches that go up and down. You got to make sure that's well labeled, what's there. I love working with electricity, even though it's deadly. So here what you see is on the left, you're supposed to secure or clamp any lines in and out, because if it's loose like that, if somebody was to bump the lines, it would rub against the metal and possibly wear away the insulation, therefore expose the live lines. On the right, you see somebody, these things are called knockouts. They're all over the panel, and that's where you run lines in and out. If you have an unused knockout, you're supposed to fill it with a plug. Just like if you have an unused switch hole, you put a cover over that as well. And these things cost like pennies to fix. So what you see here on the screen, that looks like the neutral bar. And then on the right, what you're seeing is this portion of the switches. You see the hot lines get connected here. The hot bus is right behind it. But the neutral line, looks like there's a weird looking screw there that shouldn't be there. And you see a few grounds in there as well. This is kind of a mess. Here what Todd is showing us is a line that's being secured to a metal beam by metal. Metal tends to be sharper, especially when it gets kinked, and it can actually then cut into the cord. And then if that contacts this metal beam, it would energize the metal beam. So if somebody made contact with it, they could become part of the circuit and get shocked, possibly electrocuted. Here is a lamp in which the cage is hanging open. Anything under 8 feet needs to have a cover on it when you have a bulb like that, because if the bulb was to be broken, that becomes exposed electrical. Falls are another issue, just simply because we're typically up on ladders, especially when we're doing lighting type work. And so a fall is definitely a secondary issue after you got shocked. Even if the shock didn't hurt you, it's the jump and the losing of balance that causes an injury. Burns are very common, depending on the conditions, where the pathway that the electricity travels. There's usually an inlet and an outlet burn, so you can kind of see where it went. And then doctors, they see those two things, and then they go in to see what sort of internal damage there's been. As little as 120 volts can kill you, depending on the conditions. So if you have wet skin, it's going to travel through you and kill you. If you have dry skin, you have a little bit more insulation, a little bit more. It's harder to get through you. Ohm's law you can use to dictate this kind of stuff. He has it here as current is equal to voltage divided by resistance. I always remember it as voltage is equal to current times resistance. It's the same thing as just moving things around. So VIR is what I was taught in physics, and that's what I remember. So you can calculate what the current might be. Now, this table here, I believe the person who created this was Delzine. Todd likes to talk about him. He was a university professor, and he must have given credit or something to freshmen and sophomore, and he shocked them to see what the reaction was. I'd like to see him pull that off today. So the current here is in milliamps, small amount of amps. 1 milliamp, you barely sense it. 5 milliamps, there's a slight shock, but they don't consider that painful. Men and women have a little bit different when it comes to the next level. It's anywhere from 6 to 30 milliamps, so there is actual pain, loss of muscle control, possible burn. 50 to 150, we're still under an amp here. It's still in milliamps. Severe pain, respiratory arrest, severe muscle contractions, so that's fairly severe. The next one is basically half an amp to 4 amps. And that's what you could actually shut down your heart. Death is likely. Anything above 10 amps and you're burned and probably dead. Here, Todd's getting into one major issue is when overhead cranes, we had just talked about cranes in the last thing. Anything that's up in the air, you got to be really careful, be very aware of what's around you as far as overhead lines. Because if you contact those, you can energize the metal, and it can cause serious problems. You're not even supposed to be within 10 feet of it ever. If you're going to do work on a house, whether it's siding, roofing, gutters, you may have to go near that point in which the line comes from the road to the house. I recommend you contact the electric company, the one you pay, and ask them to put guards on it. And they'll come out and do that, so that even if you accidentally tap it, it's covered with a heavy plastic. And then for anything higher, you have to be even further distance. So 10 is the minimum. So here's a picture of what happened after a dump truck with the load up backed into a power line. It blew off the tires. Here he's showing other examples. And here's the other thing too. Electricity is kind of interesting in that if you do contact a line, it kind of creates a set of circular fields, which has the high and low power or electricity in the ground. So they say that if you have to leave the cab, likely you're not in any trouble in the cab because it's traveling from the contact point into the ground. Now the ground is swelling with electricity that you can't see, is that they say either be really careful and shuffle the feet so they never leave the ground, because if there's no circuit, if there's no way for it to jump from one to the other, you won't get shocked. The other is to only have 1 foot touch at a time, so hop away or jump and have only 1 foot jump. But usually people are panicked and they take a step, and if both feet are separated and you're over one of these flux lines, the electricity will travel through you and kill you. Here's an example. I'm not going to show the rest of them because there is a person who whose corpse is burned because this forklift contacted the ground. So that's all I want to show you on that. I'm going to shift gears here. I did provide there is another presentation. I know I'm at the 20-minute mark, and I had wanted to make this shorter. Todd does a lot of the work they do has to do with temporary lighting. And so, again, these are open lines, and it could be either with Romax, it can be in conduit, it can be above the ceiling. And what he's doing is he's pointing out errors here. So he's always auditing. And here, you got a missing light bulb, exposed electrical. He tries to use a ground fault circuit interrupter on all of his lines. So if here's what ground fault circuit interrupters do. It's a technology, much like a circuit breaker, that if it detects as little as 5 milliamp difference due to an immediate release, it kills it. It kills the circuit. So it's sort of a high or fast reacting circuit breaker that is either at an outlet or connected to a circuit itself. So they're more expensive and everything. It does it by detecting like a ground difference. I think that's why it's called ground fault circuit interrupters. So it's meant to save lives, and I think it can respond within like a millisecond as well. So it's going to save lives. Yeah, you might still get a shock, but you're not going to get like muscle tense and electricity flows through you over several seconds until it does serious burns on the inside. And these are required. You could look through wherever you live. You'll probably see them in the kitchen, in the bathroom, in the basement, and in the garage. Anywhere where surfaces could be wet is where GFCI is required. On construction site, it's pretty much almost all the time. So here we have a box that's actually mounted to the ceiling versus just hanging or dangling. Here, splices are being protected. That's what you want. Anything under 8 feet needs to be guarded. Here, temporary panels, they have labeling. Everything is good. This is bad though. So here you have a cord that went through a window. Cords can never go through something that can close. It always has to be in a remained open area. Otherwise, you got to go through the wall or through the ceiling, through the floor. Whatever it is, you don't want to damage it by pinching it. Or it could be a trip hazard too, if you think about it that way. Here we've got cables held up by plastic cable ties. So one, they should be damaging the cable. Two, it would not energize the metal parts. Here we've got the proper way to use Romex, and they've got them in PVC conduit till it's above 8 feet. Here it looks like there's rope on the left, conduit on the right. Here we've got some missing outlet covers, or it's actually out. If you can see the copper or the lines, that's considered illegal. I think it needs to be under a half-inch space, but really, if you can see it, I think OSHA would cite it. Switch covers, that's a given. Ground prong removed. Extension cords, at least for these applications, must have the 3-wire type and carry more electricity. Here's a damaged strain relief, has to be taken out of service. You can't repair things, you should take them out of service. Shouldn't use Romex as an extension cord, which is interesting. So this is, again, 12-2 Romex, and it's the solid kind. You see you can bend it, and it holds its form. There's also something called stranded, which has much smaller gauged copper wires that are all twisted together. And they carry the same load of electricity. It's just they bend more freely. So like an extension cord has a threaded or a stranded set of smaller wires, whereas in the walls we tend to have more of the solid or rigid copper. Here's just an open switch spot. You can cover those for pennies. And here's the open knockout cover. It gets super easy. Oh, look at here's how you properly lock and tag a circuit in a circuit breaker panel. Pretty cool. You can't just lock a door. That's not legal. But you can block it off. Like, what are those devices they put in cars? I can't remember what they're called. But nobody could get in except for the person who has the lock. This requires a cover, but in addition, this looks like it's behind two water pipes. All junction boxes, such as the one you see on the screen, needs to be accessible, but it needs to be covered. So you can't put it behind the wall. You have to be able to access it. So here they use GFCIs on all their lines. That's good. He's showing it right here. And you can just test those too. Let's see. You do not need GFCI for two-prong, but rarely will you ever see a two-prong on a job site. Now, if you don't use GFCI, you have to use an assured grounding program. Todd does not advocate for it. It requires a lot more work, a lot more expertise. And the ground fault circuit interrupter technology is really good. I believe there's one more. We're at 25 minutes. I think what I'll do is you can go ahead and look through. Todd has I also provided some PowerPoint slides of can you find the hazard. And so please look through those. You can kind of just see it's basically cord related, spacing from cords, proper storage of cords, things like that. What I'd like to do is finish up by showing you what I've also provided you. So these are the 3 lectures. I went through 2 of them. You can look at the Spot the Hazard if you'd like. It's kind of cool. Please watch this 4.5-minute video on basic electrical safety concepts. I could spend hours and hours talking about it. This would show you what an arc flash is. I could keep going on and on. I mean, again, you could spend 8 hours just talking about arc flash protections too. But I'm trying to give you kind of the 100-foot view here. Check out the General Industry Electrical Safety Topics page. I've got a link to both the NFPA 70, which is the National Electrical Code, and the 70E, which is the Workplace Electrical Safety Code. And then I've got a link to Underwriters Laboratories, because on almost any piece of equipment that you plug into the wall, Underwriters Laboratories probably did some testing on it to verify what it's capable of doing or what it's capable of handling. And so that's something that you should be looking at to make sure something is being used as it was designed to being used, and not trying to draw too much power through it, because that could damage it. So I believe that is pretty much all I had wanted to share with you, other than if you are curious about electrical things, it's as simple as going to like a Home Depot electrical department, and you can see the different tools. I was going to show you that I've also found some wire tracers that I can actually find things in the walls. I can set the sensitivity on. I can check to see which circuit is for which outlets. I can check cable and wire. So I'm kind of adding to my toolkits when it comes to doing electrical work. So I want to do it safely, I want to do it right, I want to ensure that I know what I'm working with. So if you have any questions about electrical safety, arc flash, or just doing residential electrical work, I'd be happy to talk to you about that. But please take a look at those resources. I think doing electrical work is fun. I enjoy it, but you got to respect it. It's meant to be within the design of the panel, the switches, the lines that go to the outlets and switches. As soon as you start plugging things in, that's where the danger really lies.